So welcome back, everybody. The topic this week is try to wrap up this part on statistical resampling, which sounds like a pretty boring topic. But when you do a statistical calculation, like a variational Monte Carlo calculation, you need to provide estimates of the errors. And one thing we can do in a systematic way is something which is called a statistical error estimation. We will have more problems, as we mentioned last week, to make a proper estimate of the systematic error. So systematic error would, for instance, be the model you made for the Hamiltonian. And to find the error in that one and compare that, for instance, with experimental data is something which is much, much more difficult. But for statistical resamplings and statistical error analysis, this is something where we have pretty good tools. And last week, we discussed this bootstrap method, and we looked at a demonstration where we saw that we could reproduce the central limit theorem. So when we increased the number of data points, we saw then that a normal distribution, which we had as an initial distribution for identically distributed events, gave essentially what we expected from the central limit theorem. Now, what we are going to do today, instead of using the bootstrap method, which is often tailored to less amount of data, and also the standard bootstrap has been tailored to identically and independent results or independent stochastic variables, we are going to look at a method which is better suited for this kind of Monte Carlo samplings, and that is called the blocking method. Before we do that, I just wanted to remind you quickly of some of the things we went through last week. And then we are going to look at the way we would implement it. And in this case, as we discussed last week, my recommendation is that we take the programs which you have here. You can also find other examples online on Bootstrap and blocking and these statistical resampling techniques. If you download statistical packages, you will actually find this. And then see how we can tailor these in a post-analysis. So you would run the big Monte Carlo production calculation, and then after you're done with that, you do a post-analysis, which is a statistical analysis. And for some of you doing experiments, both of you here are doing experiments, it's pretty common then to have a long run of data, and then you do the statistical analysis after the experiment has been done. You would typically not do the statistical analysis while the experiment is running. That's less likely. Although you can use machine learning methods to correct the beam, that's pretty common now in accelerated physics. So what we are going to look at now is the basic preparation for the blocking method. And we are also going to rewrite. So this is another of these less exciting exercises. So we are going to rewrite the total variance and the total sample mean so that we can rewrite it in terms of a covariance. And this covariance measures the correlations between the data points. So as I mentioned last time, one of the things we will suffer from is an inherent error in the random number generators. So it means that the data points which we generate will have some degrees of correlations. Ideally, we would like these random numbers to be independent and identically distributed. But in order to generate them as fast as possible, you typically end up with a pseudo random number generator, and that produces correlations between the numbers. Now, the other thing is that there are also correlations between the measurements. And this is, these are things which can have to do with the physical laws which are applying. So if you have a two-body interaction, there will be correlations between two electrons or two particles in different positions. So what we are going to look at now is as I said here, after we've reminded ourselves about the central limit theorem, which we looked at last time. So I just wanted to quickly to remind you of some of these quantities. So if you have an experiment, I, and then you run J single experiments, you could think of this as an experiment you run on a regular basis. So typically you would rerun often the same experiment in order to get better statistics. So think of you collecting data one day, that could be experiment I, and that has a mean value. That specific experiment has its own sample variance. And if you look back at what we discussed last time, we don't know if the sample mean, which is this quantity of experiment I, and the sample variance of experiment I are equal to the exact variances, because we don't know the probability distribution. So our hope then is that when we make n large enough, we should be able to reach something which approaches the exact mean value if we know the distribution. If you don't know the distribution, then you simply want to sample as much as possible. And then what we are going to do next, if you think back to what we discussed last week with the central limit derivation, where we saw that if we had events which all were given by the same probability distribution, in the limit where this number of experiments I goes towards a large number of experiments, then we should approach a Gaussian distribution. If the individual distributions are independent and the events are identically distributed. So the thing which we're going to do now is actually to start with this, and we're going to look at the sample variance for a total number m of I experiments. So you could think of you running the same experiment in 10 days. That means that you would accumulate more data. When you run your Monte Carlo code in parallel, this is the same thing which happens, because you would start your Monte Carlo code with different seeds. And if you run it in parallel on 100 processors, you would then have 100 data sets. And then your average value would then be the average of all these samples. So what we're going to do now is simply to manipulate these equations for the sample mean and the sample variance. And we are going to rewrite that in terms of the so-called covariance and rephrase the covariance as an entry point to this blocking method. So many of these things are actually added here, but I'm going to repeat them on the whiteboard. And so they're just to break the monotony here, if that's okay. So I always prefer, I mean, you have all the material in the slides, but I want normally to go through them at a slower pace here. So I'm going to switch over to the whiteboard, and we are going now to derive an expression for the final variance, which then is going to have terms which look like what we had last week with the central limit theorem. The only problem is that we will have correlations between the data points because we don't know whether our stochastic events are independent and identically distributed. And this covariance is something we need to evaluate. So the question you could ask now, why don't I calculate the covariance in my Monte Carlo code? And then I'm done. Now, the problem with the covariance is that the covariance is a double loop over all your events. So to estimate the covariance, you are now doing a one loop over all the Monte Carlo cycles. To do a double loop, if you have 1 billion cycles, it means you will have 10 to the 9 squared evaluations. And you simply don't want to do that. So this blocking method is actually a method which allows you to evaluate this covariance and the correlations without doing a double loop inside your code. And you can actually do that after you've run the heavy duty variational Monte Carlo calculation. Okay, this is essentially the overarching message of what we end up doing. So you could say now in a nutshell, we don't want to evaluate the double loop inside our production code, but we do that in a post-analysis way. And even there, we don't evaluate a double loop. Okay, so let's look at the mathematics here, or this kind of small details. And as I promised you, these are not exciting things, but it's okay to have seen them. So let's, let me just set up things correctly here. So what we are going to define now is a total mean of a given number of experiments of n experiments. And that is obviously, we're going to write it like this. This is 1 over n. And this is the sum over the mean values of the individual experiments. So if you every day, if you run a specific experiment, then this experiment I, which you have here, is 1 over n. And then you have a sum over j from 1 up to n. And then I have an xij here. So that's the individual experiment which we are running. So then we can now set up the total variance. And we're simply going to manipulate these equations. So the total variance, this is again what we call the sample variance. This is given by sigma m squared. This is a quantity which we actually are going to manipulate. Because if you run in parallel, if you have m processors, this would be m experiments which you would have from your variational Monte Carlo calculation. This is obviously given by 1 over m, and then we have a sum from I equal 1 up to m. And now I'm just looking at the mean value of a given experiment minus the total mean. But I can rewrite that in terms of the individual experiments. I'm also going to introduce a new variable here, which I'm going to set up as, so if you now look at this quantity which you have here, I can now rewrite this in a more compact way. So if we now take this term here, this one, this xi minus x, that's the mean value. This is something which I can write as 1 over n, and then I have the sum over j equal 1 up to n xij minus x. I'm just simply rewriting here. So what I'm going to do now is to plug this formula into the expression for the total variance, the total sample variance. Now keep in mind that each experiment, each single experiment has its own variance. So the single experiment will have a variance which is defined in much the same way as a mean. So we're going to bring that back again. Now, what I'm going to do now is simply to rewrite the term which you see here. So I'm going to rewrite that one as an xij. And for those of you who are familiar with machine learning algorithms, it's pretty common to center your variables by subtracting the mean value. That's a pretty common technique. And many algorithms or many libraries do that by default, by just centering the around the mean value. And this is often done when you're making a fit. It's done in order to prevent that outliers can influence the quality of your fit. So this is a pretty common technique. So with that one, we have simply rewritten things. And if I then look at the sample variance, if I now plug in these variables, so let's just go back to this expression. So the sample variance, which I have, this sigma squared m, is then going to be equal to, oh, just a moment. The total sample variance is given by 1 over this m, this is the number of experiments, and n, and this has now a sum. So let me just rewrite it a little bit better here. So it's the 1 over m, and then I'm setting up the sum here, and I'm going to put this on I equal 1, experiment I, and now I'm squaring this quantity, 1 over n, so j equal 1 up to n, and this is xij tilde, and this is squared. Now, when you write this out, you are now going to get cross terms, because you have to square two sums here. So you have to square a sum. So which means that we are going to get something which will contain, I can rewrite this term in terms of a diagonal term. When you look at this sum here, so there's going to be a 1 over n, another 1 over n squared, and then I have a sum over I equal 1 up to n, and then I have the diagonal elements, j equal 1 up to n, and then I have my xij squared. But then I can reorder the non-diagonal terms. Since this is going to be symmetric, I can then reorder it with a term 2 over n and n squared. And then I have a sum over I equal 1 up to n. And now I have a double sum, but a double sum with a constraint that j is less than k up to n. And then I have my xij tilde, xik tilde. So just think back to this formula here, because when you're squaring it, this is going to be a sum over 1n squared. There will be a sum over j, and there will be a sum over k, and I would have xij multiplied with xik tilde. And then I'm just simply splitting this, so there's a double sum, and I'm simply splitting that one into one term where I have the diagonals, and then I have the non-diagonal terms. Now, another thing which we need to look at is something which I will call the total sample variance. And then I'm simply taking all the experiments I have, and I call this quantity for sigma squared 1 over mn. So now I'm just setting up this, assuming that there are no correlations in the data. I'm just taking the plain expression for the variance. And then I have xij minus this x squared. And this quantity here is simply my xij tilde squared. And you see now that I can identify one of these terms, this term here, except for the factor 1 over n, with what is called the total sample variance. So when I'm setting up these expressions, which you see here, I'm assuming now that there is no correlation between the x's. Then, if I do that, just get up and so this is something, if I use this expression, I can rewrite this formula here for sigma n. So let's do that. So this sigma m squared is then given by sigma squared divided by n plus 2 over mn. And then I have this sum over I equal 1 up to n. And then I have the double sum of j less than k. And then I have my xij, xik. And what I'm going to do now is to introduce a new variable, which I'm going to call for d. Now, these points, xij and xik, it's actually symmetric. So I can redefine a quantity which I define as the distance between two experiments. So I have an experiment J and an experiment K. So this quantity which you see here, this one, this is nothing but something which is proportional to the covariance. So if the measurements are identically distributed and there is the same, then they are independent, then the covariance is by definition equal to 0, as we discussed last time. Then your variance simply reduces to this quantity here. Now, what you see now is that if we take our Monte Carlo calculation, because we have everything ready for calculating this quantity. Now, since this quantity, which you see here, is a positive quantity, it means that if we only keep this part as the variance, we will underestimate the total variance. So it's this quantity we are looking after. But if we just look at this quantity here as our variance, and exclude any correlations between the data, then what we would get is something which is underestimating the total variance. And that means that we would get a too optimistic result for the error, because the standard deviation is the square root of this quantity which we have here, or rather this quantity. So if we leave this out, so everything which we're going to discuss now deals with us calculating this term here. So this is the excitement of today's lecture. And as you can see, this is a double sum, and you want to avoid that in your Monte Carlo calculation. But even if you calculate that one with the data set you have, if you have 1 million Monte Carlo samples, this will be 1 million squared evaluations. And even the post-analysis is going to be extremely slow. So you could just take your data sets, and if you have 1 million Monte Carlo samples, and simply compare or look at the CPU time you spend, and you will see that's going to be expensive even in the post-analysis. So this blocking method and also the bootstrap method, what they are, at least the bootstrap method, which is modified for non-independent and identically distributed numbers, try to evaluate this contribution here, so that at the end, we can provide a proper estimate of the error. This is what this is about. So I promise you, this is not the most exciting thing, but we need to evaluate these things. So when we introduce this variable, I'm also going to rewrite the sum which you see here by introducing a quantity which I'm going to call f of d. So this is just a rewrite of the second term. So I'm going to rewrite that one in terms of 1 over n and 1 over n. And then I simply introduce this variable d, which is a distance between two measurements. And then I have a 1 up to n. And then I have my summation over k from 1 up to n minus d. And what I'm doing now is simply to look at this term, and then I have x of I, and instead of k here, I actually have k, or j, I have k plus d. So I'm replacing one of these variables with a distance between the variable j and the variable k. So you can think of this as a distance between two experiments. Now, intuitively, you would expect that if you run many experiments and there is a big distance in time between two experiments, that they should not be correlated at all. So this kind of covariance measures the correlations between experiments close to each other. Ideally, you would like this quantity to be 0, but you don't have, in general, independent and identically distributed stochastic events. So then we actually need to evaluate this quantity. If I put d equal to 0, you will recognize this as a term which we have seen before. So if I put that one, then I would simply have f of 0, and that is the same as 1 over n and 1 over n. And then I have a sum over I, and then I have a sum over k, and up to n, and then I have my xik squared. And this is nothing but what we call the total sample variance sigma squared. Okay? So what I can do now is to rewrite this quantity here, since I now have introduced this way of rewriting two of the sums here. I'm still left with one of the sums. And you can see now, since I'm going from n minus up to n minus d, I can rewrite my term here now in terms of this f of d and this term here. So it means that I can now rewrite my sigma m squared equal to sigma squared divided by n plus 2 divided by n. And then I have a sum from d equal 1 up to n minus 1. And this has this function f of d. This is called, in the literature, it has actually many names, but it's called the autocovariance. It's pretty common to scale this and define the correlation function. And we could define then a function which I'm going to call k of d, which is f of d divided by sigma squared. So if I do that, you see now that this function, if I take a 0, sigma 0, that is simply equal to 1. And that will be this function k of 0. So I can then rewrite my sigma squared in terms of this correlation function. So I have a sigma squared divided by n, and then I have 1 plus 2, and then I have a function from d equal 1 up to n minus 1, and then I have this function k of d. And this function is normally called the error or contribution from correlations. So this would be the second term which you see. This one is called the correlation contribution. So if you look at this function k of d, oops, I need to charge my pen during the break here. Okay. So if you look at this function k of d here, if we make a plot of it, what you would see then is something like this. So we plot d, 1, 2, 3, etc. And then you have 1 here. So this will be the function k of d. And this is 0. So for that case, it takes an explicit value, which is 1. And then ideally, what you would see is that this function here would then just drop slowly to 0 here. Or you would actually like it to drop as quickly as possible, because that means that your Monte Carlo cycles, for each cycle, they are less correlated with each other. If you have long range correlations in your Monte Carlo calculations, you will find out that there may be a correlation function which links different types of experiments. If you then look at the plot of a similar plot of the variance, so your sigma m squared, we would start with the optimistic value where we have 0 correlation divided by n here. So this will be this value. And then when we now move on as a function of d here, 1, 2, 3, etc. Ideally, what you would like to see is that this curve here stabilizes, and the value which you have here should then be the ideal sigma m. So this is the sigma m ideal. Suppose you were able to calculate that one. This is the value you should reach as you increase this number of d. And then it flattens out. If it keeps increasing, it means that your correlations never die out. So that means that your results are really strongly correlated, and your estimate of the variance and the total variance can actually be difficult. But in general, the different Monte Carlo events are less and less correlated the more apart they are from each other. So the kind of ideal thing is actually to obtain this curve which flattens out as a function of this variable d. Now, and this variable d is something which we are going to rewrite in terms of the so-called number of blocks. So this term, which now keeps increasing here, is the term which comes from this 2 over n, and then we have the sum over d equal 1 up to n minus 1, and then we have this k of d here. So one thing which I want to do now is, when we have these results, is actually to introduce the blocking method. But before we do that, I wanted to show you again the codes and the kind of basic philosophy you would need to implement in the project here. So let's go back to the Jupyter Notebook. So if you then scroll down, so essentially what you find is the same arguments which you have here. So it's nothing particular special. And the whole thing is that you want to avoid to evaluate this specific double loop, because if you look at the definition of f of 0, this is represented by a double loop here. So there is a simple code example which allows you to do that. And you can, if you run that code, you will then find obviously that with that, you find a variance which is given by this quantity here when you then add the autocorrelation function. So this is normally called the autocorrelation. And you see that in this case, when I have only 10,000 events, this is something which is easy to run. And it goes quickly fast through the calculations. So what I did here was simply to set up a set of numbers. So I calculate the mean values, I distribute this number randomly, and then I calculate the mean value. So I just have a uniform distribution here, as you can see. And in the uniform distribution, we know that this should be equal to exactly 0.5. That's the mean value of a uniform distribution. And the variance is also something which we can calculate exactly. And that is 1 over square root of 12, which is this quantity here. So you can now see the autocorrelation function for a random number with a uniform distribution. So it starts up here. And then this, what you're looking at now, is the correlations between the random numbers you generate. Nothing more than that. So if we make this a little bit smaller, the number of data which we have. So let's do that. Now you can see more clearly. So you have 1 point when it's 0. You see that with 100 points, you don't get 0.5, and you're not getting 1 over square root of 12, but you're getting something near it. But you also see that these correlation functions, you need actually to go up to quite a distance between your measurements before the correlation function is getting close to 0. So that tells you that the random numbers, these are just random numbers. So I'm actually calculating the correlations between random numbers. And one of the tests which people use in order to assess whether the random number generator is a good one or not is to calculate the correlation function. And if that correlation function never goes to 0, then you would just discard that proposal for a random number generator. Now, the thing which we did here was simply to run this with 10,000. And if we do a 10,000 point, you will see that this is still pretty fast. But if I then want to be a little bit more ambitious here, and now suppose I do 1,000,000, then in the calculation of this specific function which we have, I'm going to have a double loop. And that is something which and you can see now it's going to take a little bit, no, it actually went pretty fast here. So you see now that my mean value is getting closer and closer to 0.5 because I have more and more points. And but you see now that, so this is just a calculation of the single loop. My correlation function takes more time because the plot is not coming up. The plot takes also some time because it's doing an evaluation for 1,000,000 points. But in this specific case, it's still now calculating this quantity here. And you can see that from my kernel here that is still running. So the single loop case, which we have when we calculate the variance and the mean value, which are these here, they come up immediately, but it still takes time to get the autocorrelation function. And this is a typical example of what we will have to face when we run these type of calculations. And that's why the blocking method is a way to circumvent the calculation of a double loop. So let's just wait a little bit and see if this comes up because it's still running. So it's going to take some time to see this correlation function. But hopefully you would like this to be as close to 0 as soon as possible. This is only for the random number generator. Then if you look at your physics case, there will be correlations in your data sets for your physics calculation. And that's something which is due to the laws of motion which you're implementing and the forces you're implementing. So you will have correlations among the random numbers, which you hope are as small as possible. So that's a source of contribution to the covariance matrix. And then there will also be correlations among the data points, the physics points which you're dealing with. And you can see that this is still running here. So we can just wait a little bit when we did 1 million points. And that's why, even though it sounds tempting to calculate exactly the autocorrelation function, this is something when you have millions of Monte Carlo cycles, which can take a lot of time, even for the post-analysis. Or maybe I'm going to stop this because this is, so you see the variables here, actually this is pretty close to the square root of 1/12, but and also the mean value is getting pretty good. So when you are now looking at the standard deviation, this standard deviation needs to be augmented with the calculation of the correlation function. So one thing I wanted to do before I wanted to take this after the break. So one thing I wanted to remind you of is how you would run the calculations in project number 1 when you're doing the resampling of the data. So the code here is this code for 2 electrons in a quantum dot in a harmonic oscillator trap in 2 dimensions, and they're interacting with a Coulomb interaction. This is the example which I've been using throughout the semester. And then there's a trial wave function, there's a local energy, which now contains also the derivative of the Jastrow factor. There is a derivative of the wave function with respect to the parameters alpha and beta, because this is a case where I have 2 parameters. I calculate the quantum force. I have the energy derivative, the expectation value of that, as we discussed previously. So I'm not going to repeat everything. There's a function which calculates the energy. And then what I'm doing is that for every calculation of the energy here, when I'm doing my production run, so I have the number of particles, 2 dimensions, I initialize the random number generator. And in the first calculation, I'm actually only running with few Monte Carlo cycles. So this is my runs for finding the optimal values of the parameters, where I give a guess of 0.9 and 0.2. And then I minimize the energy. And then I find the optimal parameters. And today I will also explain to you why these blocking methods is normally run in powers of 2 to the power of something of number of Monte Carlo cycles. Because we divide it in blocks by splitting the data in 2 every time. So then it's convenient. So I can actually set up 19 such repetitions where I divide my data set in 2. And the final code here, when you run it, produces a final result. And now we should, I think this, I shouldn't have started this correlation piece because that's going to take time actually. So maybe I just stop it. Let's see. Yeah, this is still, let me just go up here. Yeah, no, let me just stop the kernel here. Restart and clear all outputs. Let's do that. Because this, you see now the correlation function, I'm calculating the this with 1 million Monte Carlo cycles. I'm actually doing 1 million squared evaluation. And that's going to take a lot of time. So this simply motivates why you should not use a brute force calculation, but rather use these techniques like the blocking technique. So let's now look at the Monte Carlo calculation here and run that one, because that's a little bit faster. And then when you have run that one and found the energies, then with the production run, then you can do the final resampling analysis afterwards. So this is still, here we are. So this is my final analysis. And it's now, after it has done that, it used 2 iterations to find the optimal values. And now it's running the final Monte Carlo calculation with just the optimal parameters, which I found from these calculations. And you have the optimal parameters here. And this is the final energy. But then I'm going to run now a calculation with 2 to the 19 Monte Carlo cycles. And then it's going to produce the final results. And with the final results, I can use my blocking analysis. And with that one, I can now estimate the final mean value, which is 3.002, which is pretty good because the exact result, you can solve this analytically, it's 3.0. And this is my standard deviation. So when I'm going to present these results, I would write 3.02 or something plus minus 0.0025. So after all these long exercises, what we are aiming at is just a way to efficiently calculate this final number. So I hope you can see the same excitement which I see with just producing this final. But hopefully by running this code for the correlation function, you saw that if you, in a brute force way, just increase the number of samples, and like in this case here, you have something close to 1 million of Monte Carlo cycles, then if you were to calculate the correlation function, that would be extremely slow. So after the break, we are going to look at the blocking algorithm. And when we're done with that, there is a final thing which we need to discuss with the project, and that's something which is called the one-body densities. And I updated the project, so we have the deadline on March 31 instead of next Friday, but then on Monday. And I also took out and made optional the parallelization part, since most of you are actually coding in Python. So let's take a small break. So before the break, we discussed the so-called correlation function, and we tried to motivate for why we need to evaluate that one. And the last figure here actually gives you roughly what is going on. And if we leave out the correlation part, because we will have correlations among the data points, this means that we will have an over-optimistic estimation of the error. So last week, for instance, I run the error estimation or the standard deviation with a bootstrap method, which is based on independent and identically distributed an assumption about that. And in that case, we found that there was a difference between the blocking method and the bootstrap method, because the bootstrap method gave us a standard deviation which was pretty close to this number. So the blocking method is a recipe where you're actually converging to a fixed point, but where you can update iteratively the calculation of this correlation term without having to evaluate a double loop. So let's look at some of the basic ingredients of the blocking method. For statistical evaluation of the standard deviation. And the quantity we are looking at is the STD, which is again what we last time called the standard deviation, which is the square root of the total sample variance. So the method is actually a method where we split the data in blocks of 2 all the time. And basically what we are going to do then, by splitting the data like this, we are going to make an estimation of the standard deviation and the correlation function. So we have a data set. Suppose this is a data set. So we have an x0, there is an x1 up to some xn minus 1. What we typically would do then is to split the data set in first 2 blocks. So it's an iterated splitting. Into blocks of half the size of the original data. So what does it mean? So we would now define an x prime, which has n prime data points, which is 1/2 divided by n, times n points. So that means that we are going to define an x0 prime, which is given by x0 plus x1 divided by 2. We're going to have an x1 prime, which is x2 plus x3 divided by 2, etc. So we are then going to have the number of Monte Carlo cycles or Monte Carlo samples will typically be given in powers of 2. Now powers of base 2, 2 to the power of p. So let me just show you a simple example here. And where we now take, let's suppose now that we have some few data points. So let's now look at this simple example here. So suppose that the original data set is this impressive series of numbers, 1, 2, 3, 4, 5, 6, like that. If I now calculate the mean value of this quantity, the mean value, the sample mean, which is 1 over 6 of I equal 1 up to 6 of x of I. If we do the mathematics here, that should be given 7/2. Now, the type of transformations of data should not change the mean value or the variance. So it does not change the expectation values because we're just changing the variables here. So in general, what we would have is something like an x of I prime, which is just 1/2. And then I have an x 2I minus 1 plus x2 of I. That's the general formula. Now, what I can do now, I can split my data. So I have 6 numbers. I can split my data in 3 blocks. Okay. So I would then, if I take this recipe, I can now define a new data set of x1 plus x2 divided by 2, x2, 3 plus x4 divided by 2, and then I have x5 plus x6 divided by 2 here. Now, if I then calculate the mean value of this mu prime, then I would get 1 divided by 3, and I have I equal 1 up to 3, and then I have my xi prime, and you would find that this is 7 divided by 2, as it should be. So the quantities like the variance and the mean values, these are quantities even with these transformations, because we're not doing anything but just transforming the data set, they should be conserved. You can look at the variance as well. So if we take that quantity and calculate this with these 2 data sets, we are going to get exactly the same number. So let's just do that. And so let's take the variance. And so the variance with mu is then clearly 1 divided by 6. And then I have a sum from I equal 1 to 6. And then I have x of I minus, and then I have mu, which is 7/3 divided by 7 divided by 2. And if I calculate, if I put in the numbers, I'm going to get 8 divided by 3. If I now do the sigma prime with mu prime, this is actually 1 divided by 3. And then I have a sum from I equal 1 up to 3. And then I have these different numbers of x2 of I minus 1 plus x2 of I divided by 2 squared. And this is minus mu prime squared. And if you do the math again, you will get that this is equal to 8 divided by 3. So if you do the full calculations here, then you will obviously get something which is conserved here. And it means that we are now going to try to manipulate this equation here in a specific way. So we are going to set up different divisions by 2. So we will have data sets now where we will follow this expression which you see here, where we can divide it by 2 the first time, and then we get a new data set, double prime, which is actually this data set divided by 2. So this is why also we try to have a number of data which go like 2 to the power of something, because then we can keep doing these divisions by 2. So the whole thing we are doing now when we are bringing these numbers together is that we are also evaluating contributions in terms of a larger set of data points. So the way we are going to set these things up is then to define first a mu0, which is simply the full data set, 1 divided by n, and this is a sum of I up to n, and we have the data points x of I. So that's the mu0. And in general, we will have a mu of I, and I is the number of times we do these operations. It's also going to be called the number of blocks, because you see now that in the first case, you could think of these 6 numbers as just 1 block of data, okay? Then when I divide that 6 by 2, I have 2 blocks, because I have variables now which are defined in terms of 2 numbers set together. So I would call this prime result here as a result with 2 blocks. The first result here is just all the data sets, so that's just 1 block. So when I evaluate my different quantities. So then this mu of I here is actually the I represents the number of times we have divided by 2 to the power of I. So mu of I is then simply 1 divided by n of I, and the sum from I equal 1 up to n of I. I should put a j here, and then I have my x of j of I. And this n of I is now simply the original number divided by 2 to the power of I. Okay? So these are just definitions which I'm bringing in here. So this means also, and if you look at the example which I did here, my total variance should stay the same when I make these transformations. So if I do this sigma m squared of mu 0, that should be the same as sigma m squared of mu of I. So now I'm just putting mu as the average value, which I have for a given number of blocks. And obviously this one has to be the same. So these are conserved quantities. So this is invariance. Then what you can do, you can actually rewrite following very much the same recipe which we did before the break. And this is what was done by Flyvbjerg and Petersen. There's a paper back in 1989, and it's linked in the lecture notes together with Mario's paper. So Mario's was a student who actually improved their formula. What you can do then is to rewrite the sigma squared of mu. And now this is the exact one. So when I don't put any label, and it should be the same. So this is the quantity which I just rewrite in a simpler way. I'm taking away this n, and I'm setting up the way it looks like. So this is the one calculated for a given number of blocks squared divided by n of k. So this looks pretty close to what we had before, plus 2 divided by n of k. And then there is a formula which you can then set up to evaluate the contribution from the correlation part. And I'm going to set up this h, what that one actually is. And this is an n of, so this is a k here, k. And this is an n, no, sorry, this is a sum of, what did I do now? Yeah, h. And this is n of k. And it's multiplied by a quantity which is given by this one and a function of h. And I'm going to set up what that is. So this function gamma of k of h is the same as the covariance, which we have defined earlier, of x of I of k, and then I have x of j plus h of k. And this function h plays the same role as the one we defined earlier, of I minus j. So this formula, which you see, is essentially the same thing as we had before. Now, this equation for, you can show that this equation for gamma, which we put up here, this gamma of k plus 1, is something you can evaluate as you move on. So this can be written, I'm just stating the final result here without going through the explicit derivations. So this should be equal to 1 over a half of k, 2 times h, and plus 1/2 of gamma of k. And this should be in here, this should be 2h plus 1. And then I have, in case h is 0, and then I have 1 divided by 4 of gamma of k. So I'm just stating the result, plus 1/2 of gamma of k of 2h plus 1 over 4 of gamma of k of 2h plus 1. So you can use previous results to calculate these quantities. So I'm not going to go through the derivations, but you can show, if you plug in examples, that you can then start by evaluating the result with one block only. So if you evaluate here, what we are going to get is something which looks like this. If we make a plot of the results, so we would now have a 0 here. So actually with 1, and then we have the 2, etc., 3. And this is something which we call the number of blocks. And then when we now have the 0th value, this could be a value where we now have simply evaluated sigma squared divided by n. Then when we go to the next point up here, this is this point, then we have, actually, sorry, I did something wrong here. So when I have 1, then I'm simply evaluating. So with 1, then I have the full data set. So this is n of 1, which is actually the full data set. Then my result, the quantity I evaluate, is this sigma squared divided by n with no correlation function. So the way it's evaluated is that you are constructing the covariance step by step by making this block subdivision. So when I go to the next point, then I would have for 2 here, I would then, no, wait. And yeah, I've been confusing myself here. Sorry, I'm confusing myself. I was looking at the wrong thing here. So let me do that. Sorry. This is 0. Then I have 1, 2, 3, etc. So in this specific case, I'm using the full data set. Then when I get to 1, in that specific case, I'm evaluating this quantity sigma m squared. And in this specific case, I have n prime equal to 1/2 times n. Then the next case, I have n double prime, which is equal to n2, which is then the same as 1/2 of n1. So this is n1 here, which is the same as n prime. And when I do this calculation, my estimation of the correlation function is given now by an increasing number. And then when I keep increasing these divisions by 2, I will reach a point where this flattens out. And this is the number of blocks, which simply says that in a statistical sampling way, it means that the elements in a specific block, they are basically independent from the observations in another block. Because when you make the block larger and larger, you have more and more observations. And that means that these observations become statistically almost independent of the next block of observations. So the recipe for calculating this function is done iteratively. So instead of having a double sum here, you actually evaluate these contributions sigma k, these terms here, iteratively. And then by these subsequent divisions by 2, you end up with a final result where the curve starts flattening out. And that's when you have reached the ideal value for your standard deviation. Now, the code which you find in the lecture notes is something which you should feel free to use. I'm not sure if the blocking algorithm is included in standard resampling packages. I actually don't remember. I have not looked up the root package, whether it has these resampling techniques. But in that case, you can use the codes which you find in the Jupyter notebook. So in our case, this forms more a kind of background material, but it is an iterative way by which we can then find an estimation of the covariance step by step without having to evaluate a double loop. And you saw from that simple example we had before the break, you saw that we were actually getting quite some involved calculations in order to evaluate it if we have 1 million samples, because then we would have a double loop with 1 million samples, which means 1 million to the power of 2. And we would like to avoid that. So this is a very efficient way by which we can evaluate the standard deviation in an uncomplicated way. And it's typically recommended when you have large data sets. When you have small data sets, it's common to use the bootstrap method. Because with small data sets, the bootstrap is computationally very efficient as well. Whereas when you go to large data sets, as you have in a Monte Carlo sampling, then the bootstrap becomes computationally much more involved than the blocking method. So this is the basic method which we are going to use. I wanted to end this lecture by a discussion of a quantity which we will need in project number 1. And this is a very useful quantity which is used to study correlations in quantum mechanical systems. So this is called the one-body density. This is also something you would do after the optimization. So after optimization. And the variational Monte Carlo calculation and VMC calculation. Because that's when you have the optimal parameters. So that means we have then, let me write it down. We have then psi of t, the trial wave function, which depends on the positions. And then I'm going to put a hat on here to indicate that the hat is the optimal parameter you have found in the calculations. This means that you have the best possible representation of your ground state energy of the system. So what you're going to do then is then to calculate the one-body density, which is defined as follows. We integrate away all the other particle degrees of freedom. So that means that you define a quantity which then depends on only, let's say, particle 1, It's irrespective which one you pick. You can pick whichever coordinate, but then the integral which you have to evaluate is a multidimensional integral over the different particles which are not included. Actually, you integrated away all but one. And this is then multiplied with the wave function squared. This is your trial wave function, and then you have R1, R2, up to Rn. And then you have this one for the optimal parameters, and this is just squared. In 2 dimensions, then you have to be careful, because then this Ri is just one of these. It's just given by the unit vector times x plus the unit vector times y here. So E of x and E of y are the unit vectors. So it means that, like in our case, since we're looking at the ground state is normally isotropic. So that means that we don't need to think of the angles. So this is something which will simplify the calculation of the one-body density. So we are looking at the one-body density of the ground state wave function. So if you do that, then your density here, rho 1, which I'm going to just rewrite as a rho of r, this is going to be given by a function which depends on x and y. So this is my rho. And in our case, we can now use, that r is given by x squared plus y squared. And the function is isotropic. We assume ground state is isotropic, so we don't need to deal with the angle. Isotropic. That means that if you want to be fully precise, in 2 dimensions, you would have to multiply this quantity with 2 pi, because you would integrate away the angle. So there is a 2 pi factor which you need to account for if you want to have the precise expression. If you are in 3 dimensions, there's a factor of 4 times pi, which you need to include, because you're integrating over the angle theta, which goes from 0 to pi, and then the angle phi, which goes from 0 to 2 pi. So then you will get 4 times pi squared actually, so which you need to include. Now, if we assume that the ground state is isotropic, we're actually going to let this quantity xy here, we just let that one go over to a function of rho of r. But for 2 dimensions, we would then need to take into account x and y, so you would make an array of x and y values. Because your wave function, which you're plugging in, the Monte Carlo wave function you obtain, is going to be a function which depends on the Cartesian coordinates, x, y, and z. So when you're going to perform the plot of this and set up this rho of r like this, you would need to have an array of elements, x and y, or positions. You can pick this randomly, or you can just set up a discrete mesh where you set up these values, sorry. So the interesting thing then for us is the following. So let's just set this up. And if I plot this rho of r, so r here, what you would typically get is something like this. So this is the likelihood of finding one particle as a position of r. And keep in mind now for the ground state, it's isotropic in space, so it has the same value depending on the angles. If you think back of the hydrogen atom, in the ground state, it depends only on r in spherical coordinates. So it has a wave function which goes like the exponential of minus alpha times r, multiplied with a normalization constant, which comes from the 2 angles, which is 1 over square root of 4 pi. So if you make a plot, a typical wave function with one-body density, which you would get, could be something like this. So this could be the case with harmonic oscillator only. So let's just write it with HO, harmonic oscillator, no interaction. Now, this is a function. If you now have found the optimal value of alpha, for project one, you know that this is just a product of harmonic oscillator wave functions. So in that specific case, for the non-interacting case, there is no point in actually performing this multidimensional integral. So if you now think of the harmonic oscillator, so the non-interacting case, so let me just set that one up. And now I'm setting this up without the normalization constant. We're just leaving that out, because that is just a constant you would multiply the final one-body density with. Then we have the single particle wave function of R, I, which is proportional to e to the power of minus alpha, and then it's Ri squared, okay? This is the answers which we have chosen, and if we put in alpha prime, no, alpha hat is the way we have written it is given by 1/2, okay? And you've seen this in the calculations. So that means that if I have, let's say, two particles, with two particles only, what you need then to integrate is a d of R2 in 2 dimensions. And then it will be e to the minus alpha. We put a hat here. And then we have R1 squared plus R2 squared. And since this is squared, there is a factor of 2 here. Okay? So this is the integral we need to evaluate. And in our case, that becomes simply, if we now transform to spherical coordinates, not to polar coordinates, this would simply be given by 2 pi, and then we have a d of r, R2, there's no vector here, and then there's an R2, and then I have an e of minus alpha, and R1 is not included, times 2 here, and then there is a new factor, plus, and then I have a x2 squared, no, so sorry, R2 squared. Let me just rewrite it correct. Minus 2 times alpha, and then we have R1 squared plus R2 squared. So that's the integral which we need to evaluate. And this is an integral which you can look up, and it's an integral now which goes from 0 to infinity. And you can actually look that one up in tables. So this is something which you don't need to perform a Monte Carlo calculation on. If you want to test that your Monte Carlo calculation is doing the correct thing, you can always replace this integral here with your code. But it becomes more interesting when you have a interacting case, because then you would have to evaluate these integrals numerically. So for the non-interacting case with 2 particles, if you add more particles, you just get more of these integrals. So if you have, let's say, 10 particles, you would have to integrate R2, R3 up to R10, and then you would have R2, R3 squared, etc., etc. Okay? So this is a useful test, and you would typically plot that one like this. Now let me see now if I can trigger your intuition now. So suppose now I add the interaction and I get something like this. So this is with interaction. And this is why the one body density is actually very interesting, because you can extract experimental information. If you have charged particles, you can have the charge density you can extract information about. And you can compare a theoretical one body density with, let's say, an experimentally extracted one body density. And if you now add an interaction, you could get something like that, or you could perhaps get something which looks like this. It gets changed. I've exaggerated. So if you now think of these two cases, what kind of interaction would you think this represents? If you look at the red one, so particles get pushed out, right? Yeah. This is repulsive. So, and what you would typically do then in a theory analysis, when you link that with experimental data, is that you plug in the non-interacting case. If you now believe that your particles move in a harmonic oscillator, then you would say that if there is no interaction, then the blue line should be what you should get. And when you compare with the experiment, hopefully that is what you get. Then if you plot the one body density with the interactions, you can get repulsive. And then clearly this one has to be an attractive, because then the particles get pulled in. On the other one, they get pushed out. So the one body density and also the two body densities, they are often used as a measure of correlations. And you will see now that in your specific case, when you have a repulsive interaction, you will actually get a curve which is going to be pretty close to the non-interacting case. It's going to be a little bit out. And that is also a measure of whether the correlations induced by the interaction are strong or not. So if you have a small deviation from the non-interacting case, that is an indication that your force is not very much influencing the system. If, however, there are large deviations between the interacting case and the non-interacting case, that's a clear signal of the strength of correlations, which are induced by your forces. So the one body density is one of these measures, which often is used to analyze the wave functions which you get, and then extract some information about the forces. And if you have experimental data on one body densities, charge densities typically, then you can actually compare your theoretical model with experiment. And that is extremely useful. So in solid state physics, you can often extract information about one body densities. You can extract information about one body densities from nuclei as well. And this is something which has been done over many, many years where people try to compare theory model with experimental data. So this is a technical thing where you actually need to integrate. And for the integration here, we don't need to do that for all the 100 plus particles, because that will typically take more time. So it would suffice just to illustrate this for some few cases. That sound okay? So you would need to make a table of X and Y values if you're in 2 dimensions. If you're in 3 dimensions, you would need to make a table of X, Y, and Z. And these values define the value of R. And you could use those to calculate that integral, because you need to tabulate this rho of R, which we have here, this one, as a function of R. So you don't plot it in terms of X and Y, or X, Y, and Z, but you plot it in simply using the polar coordinates or the spherical coordinates. Since this function for the ground state, for the systems we are looking at, is isotropic in space, so there is no dependence on the angles. So we don't need to plot the 2 angles in 3 dimensions or the one polar angle in 2 dimensions. That's simply not needed because it's going to look the same. So this would be one of the final plots we make. And we decided to leave the parallelization part as optional for you who write codes in Python. So then we should essentially have all the elements which are needed. And then we use the rest of the day for discussing the project. And okay, any questions so far?